Hello, hello. So, hello,
Hi.
Geraud. How are you doing today?
I'm good. I'm good. And you?
I'm okay. Um, so let's wait that people come. Let's wait that people join us on the live stream.
That's good.
Yeah, we can wait 5 to 10 minutes, so we can either start at 5 minutes past eight or yeah, 10 minutes past eight, 8 p.m. my time. So that's GMT
Yeah.
plus.
Uh, 8 p.m. your time. Wait, are you the same? Are you the same time zone as me?
Yes, I
Uh,
think with South Africa we are in the same time zone. I mean, we don't have the same weather, but we are
mm,
in the same time.
yeah. I think that makes sense. Hi, Saskia.
Hello, Saskia.
Yeah, I think it's fair to wait for a few more minutes. That was the same in the last couple
Okay.
presentations.
If it's fine by you, it's fine by me. So,
You are the host, so I'm following your lead.
well,
Mm,
without a presenter, I'm kind of useless here. So,
uh,
hello, everyone who is joining. We'll still wait a couple of minutes. Let's say 10 minutes past eight, 8 p.m. my time, and we will be starting. So how have you been enjoying being the host for KmerAI so far?
That is a that is a difficult question. It has been pretty fun, but the time, I think that the time at which this presentation has happened is like a tough one for everyone.
Okay. I mean,
But other than that,
it's good to know so we can discuss how to choose a better time that
yeah,
suits like a lot of people.
yeah, yeah. I think especially the weekend. I think like we chose, or you guys chose the weekends because to kind of like so that everyone will have some time. But actually, I think it's the opposite. Uh, I think like people, probably usually have plans during their weekends, and so they end up just watching the presentations after, uh, and not live.
I actually saw. I was thinking about it today and thought, maybe that's why a lot of people, like a lot of YouTubers. I mean, we are not doing this to be famous on
Mm,
YouTube, but a lot of YouTubers prefer to, like, instead of live streaming, they just post it after so that people can watch at their desired time. But the question of, or yeah, the reason for Saturday was because we thought during the week people are working, so it's difficult
yeah,
for someone to. I mean, at what time would people present during the break time, or when they come back home? They are tired. For some people, they have kids, etc. So we thought that's difficult. And then Sunday, we thought, I mean, let's give people their Sunday.
yeah, yeah,
So,
exactly. It is a
yeah,
tough one, especially with like multiple time zones too. It's
yeah,
difficult.
I think maybe morning, Saturday morning would have been interesting because at this time people could be, I don't know, outside. But again, the time zone issue, because if we do it in the morning, then in Canada, etc., I mean, morning like GMT plus 2 or GMT plus 1, but that in Canada would be middle of the night. Hi,
Yep,
Tio Academy. Hi, Kochi.
exactly. Hello, hey guys.
Hey, Simo. Good to have you here.
Hey,
We are starting in 1 minute. So, in exactly 1 minute, we will get a presentation from Geraud Nangue, a very hard one. So, you guys should prepare. When you told me the other day, oh, I was thinking of doing like a
mm,
presentation on a bunch of things, I was like, you're joking. You can do multiple presentations. Why do you want to do one presentation and present
mm.
everything? Do not kill us. Sorry.
So yeah, it is kind of like counter. It's kind of like the opposite actually. Like the presentation I was going to do was going to be kind of like high level, basically touching kind of like touching a couple of things. Right? So it was going to be more of like a storyline of like various research and the whys and like the stuff that we have done. And so it wasn't going to be that technical. But now this one is focused on one. It's focused on one paper. So I try to leave as much math as possible. Actually, I think we barely have any math here, but it is. So of course, I'm going to go to like, the details of the approach. At least like as much as it can fit, like 45 minutes or so. And so yes, it's actually the opposite. If I did when with the previous presentation, it was actually going to be less technical and more the lay of the land of the real research.
I see, but I think this format would then be good because, yeah, we really want people to showcase their work, their efforts. And I mean, no matter how technical it is, or it's fine.
Yeah,
You
but yeah, people shouldn't worry. It won't be as technical as the previous presentations, at
okay?
least.
Okay, I think we can start. Um, so, thank you, Geraud, for accepting to present your work today with us at KmerAI on skill machines temporal logic skill composition in reinforcement learning. So, we have two formats. Either you take questions during the presentation or you take questions at the end of the presentation.
Yeah,
Can
so
you hear
I
me?
think we can go with, yeah, I can hear you. It's just that the streaming is laggy a bit. But now it's moved. Uh,
Yeah.
yeah, I prefer at the end of the presentation actually, so that we can have as many questions as
Okay.
needed,
Okay.
and we
Okay.
can try and make the presentation as concise as possible.
Perfect then. So I'll go ahead to give a brief introduction about who Geraud is. So Geraud is an IBM PhD fellow, a PhD candidate and lecturer at the University of Witwatersrand. So he has always been fascinated by the immense potential, for good of creating intelligent systems, the pinnacle of which is artificial general intelligence. So his main research interests lie in reinforcement learning because, as according to him, it's the subfield of machine learning which he believes has the most potential for achieving artificial general intelligence. I will come back to that sometime at the end because there are a lot of things about AGI and if it's really reachable, but we can come back to it later on. So, Gero is in particular focuses on principled approaches for efficient compositional generalization in reinforcement learning agents. So, please, Gero, you have the floor.
Awesome. Thanks a lot for the nice presentation and nice introduction, and thanks a lot for the opportunity to present my research here to in KmerAI. Okay, so yeah, so today I'll be presenting work that was recently published at ICLR 2024. So that happened in May in in Austria. And so the title is Skill Machines, Temporal Logic Skill Composition in Reinforcement Learning. So this is work done at the Ray Lab at the University of David Watersrand with Devon Travis, Stephen James, and Benjamin Rossman too. Cool. So one of the ultimate goals of reinforcement learning is to kind of one day have generally purpose robots, right, that can help us in various tasks in the real world or in various environments. So you can imagine, for example, you can imagine, for example, a domestic robot that will kind of like helping with various chores or cooking and etc. in at home. And so imagine, for example, you have such a domestic robot in an office environment or like an office robot, and in your office you have various things, right? You have like various rooms, you have like a coffee station, you have expensive decorations in the room, you have like a mail room, you have like an office room where people work, and so on. I imagine that this blue dot here represents your robot. And so the several tasks you may want your robot to kind of solve in this single environment. For example, you may want the robot to deliver mail to the office until there's no mail left. And then you may want the agent to deliver coffee to the office until there's no one in the office. And finally, you may want the agent to kind of like patrol each room from room A to B to C to D, and then back just to kind of like make sure that no one else needs help with anything, and also kind of like checking that things are fine across the office, right? And you may want the agent to do all of that while never breaking any decoration, right? Because the decorations are presumably extremely expensive. And so you kind of want a safety aspect incorporated into the way the robot is solving the task. So this is a very long horizon task, right? It's like extremely long. Several things involved here, safety aspects and goal-reaching aspects. And there's several such tasks that you can imagine you may want the robot to solve in this one very simple environment. So one challenge, so the goal is to kind of eventually have algorithms that are able to kind of like create such agents. But there's a number of challenges right now in reinforcement learning to achieve this goal. The first one is that usually learning is very slow in reinforcement learning. Right? So usually, given a single task, you have to learn it from scratch, right? And so if you have multiple tasks, you have to learn each one independently. And learning each one of them usually takes enormous interactions with the environment. So it is very sample inefficient. So sample efficiency in RL is trash. And so you kind of like ideally want to be able to transfer knowledge between tasks that you have solved to new tasks that are presented to you. The second challenge is that of task definition. And so what do we mean by what the task the engine needs to solve? In reinforcement learning, it's usually defined in terms of the reward functions. So the agent may receive a reward of plus 10, for example, when it achieves the desired goal. But defining such tasks or such reward functions requires expert knowledge, right? Because this is a single scalar signal you give to the agent for each interaction it has with the environment. And somehow those single scalar rewards in combination should kind of represent the desired behavior that you want your agent to learn. So usually it requires expert knowledge. And so usually you kind of like, even if you're an expert, you kind of have to like be fine-tuning that reward function to kind of get the behavior you want the agent to learn. And often this also leads to unintended side effects, also called reward hacking. When the agent learns a behavior which is not the behavior that you were intending for it to learn from the reward function you had defined. Right? So the agent has kind of somehow hacked the reward function that you gave it and figure out a different way to a different type of behavior to optimize based on that reward function. So that's the second challenge, right? And so maybe like one thing that we may want is to, instead of defining the task based on rewards, we may want to define the task symbolically, right? A bit like language. The third challenge is that solving tasks is extremely hard. How can agents solve tasks requiring like hundreds of actions, hundreds of interactions with the environment? And also, how can they do that with guarantees on their behaviors? Right? Because, of course, if we kind of eventually want to have robots that helps us with various tasks in the real world, we kind of want some guarantees into the behaviors that they are using in the environment, right? Or that they are demonstrating in the environment. So let's cover the third challenge. Right? Can we guarantee that our agent will behave appropriately in an environment? So ultimately, we want to specify tasks in a human understandable manner, right? So that we can understand the tasks that the agent needs to solve, but then the agent also needs to kind of like have the correct understanding of the task that we want it to solve. And second, we kind of don't want to have to be relearning every single new task, right? That is not how human beings are general. You know, human beings are able to leverage prior knowledge to learn or solve new tasks much faster or even immediately if possible. So we kind of ideally want that from our agents. And we also want to be able to do all of that provably, right? Have these guarantees in their behaviors. And so one promising approach in the literature is to kind of use reinforcement learning to at least frame the setting of an embodied agent making decisions in an environment. And so this diagram here kind of represents the usual reinforcement learning loop. You have your agent here. You can imagine it is like a cute little robot. It takes actions in the environment. The environment could maybe like be the real world. And then it receives feedback from the environment in the form of observation. So then it has taken an action. What is the next observation it sees? Right? And also a scalar reward that kind of represents the task that it needs to be solving. And then it continues, right? Given the new observation, it takes another action in the environment and so on. So that is the reinforcement learning loop. And so there's a couple of terms here. I think this is going to be the last slide where we see some formal maths. The other slides we kind of include some maths, but not so formal. But just these three main quantities are kind of like useful for us as we're going forward. The first is the policy that the agent uses to act in the environment. So this is a function of state and action, and it basically says what's the probability of taking a given action at the current state, right, in the environment. And the state is, you can think of that as observation that the agent sees from the environment. So that is the policy. This Q part here is the action value function. Essentially, it says that if an agent is at the current state and then it takes an action, what is the cumulative expected future rewards that it will receive? Right? So this is the expectation. This is the rewards it gets right now for taking that action at the current state. And then we are just taking the cumulative discounted rewards going into the future, all right, while following this policy pi. So that is what we call an action value function. And then we can define the optimal policy pi star as basically just being the policy that maximizes that action value function. Right? There's also like a related quantity called Q star, which is just the optimal action value function. So those are the three of useful terms, very basic terms that are used throughout reinforcement learning. And so essentially, pi star, at least in regular reinforcement learning, represents the solution to a single task. And this is very important, all right? So it means that if you're in a setting where there's multiple tasks your agent needs to solve, you have to like learn pi star for every single one of those tasks. Right? And it's extremely sample inefficient. So let's first start by talking about how do you specify tasks in a symbolic manner in reinforcement learning. So I mentioned earlier that you could probably want to use language, right? And the popular way of doing this, at least in RL, is to use formal language. So we kind of call this a temporal logic task specification. An example of such a formal language is linear temporal logic. And essentially, it will define the task an agent needs to solve by basically using logical operators like negation and intersection, and also like some temporal operators like next do A, where A represents like some task, or eventually do A, or always do B, right, and so on. Here, I'm just pictorially showing what these operators mean. So, for example, A just means right now I want A to be true. Forever A basically means that you want A to always be true in the entire trajectory of the agent. Eventually do A basically means that you want eventually in the trajectory of the agent, you want eventually that A be true, right? So you can imagine, for example, if you want the robot to go make a cup of coffee, you want that as the robot acting in the environment, eventually it reaches the state where it has made the cup of coffee. Right? So that's what eventually means, and so on. So that is a formal language, specifically linear temporal logic. And so if you imagine, for example, this simple toy robotic environment where you have like a robot here, it is a point mass robot, so it can only take like, it has like, it has two actions it can take, continuous actions. One is the angle that it wants to rotate at, and the other is the force that it wants to exert. Uh, and the other is a force that it wants to exert. Right? And it also has sensors, so it can sense like these buttons here. It can also sense these blue regions, and it can also sense this red cylinder. Right? And so essentially, there's kind of like three propositions in this environment, three type of like objects in this environment that you can define your task over. One is the button, the second is like the cylinder, and the third is the blue region. Right? And so you can say, for example, that you want the robot to, let's say, navigate to a button and then to a cylinder while never entering blue regions. So that's an example of a task that you can give the agent in this environment. And in terms of formal language using LTL, it will be kind of like represented like this, right? Using this formal expression here. It's not necessary for you to kind of like fully understand how to read this expression. You can just keep this natural language interpretation of the task in your mind. So that is a specification of the task. How do you now convert this to an actual reward function? Right? Because ultimately, the agent learns in reinforcement learning. An agent learns from rewards. So you can convert the specification into a reward function by using something called reward machines. And essentially, these are final state machines that represents the reward function for the given task. So for example, here it is saying that for any transition, so it starts here at new node. For any transition the agent makes, it just receives a reward of 0. Right? So for example, if it sees a button and it hasn't entered the blue region, it receives a reward of 0. And then it moves to U1. If it sees a decoration, if it enters a blue region, if it enters a blue region, then it terminates. And if it reaches the cylinder without entering the blue region, then it receives a reward of 1 and terminates. Right? So it's just a state machine that represents a reward function for the given task. Uh, cool. So essentially, this solves the specification aspect of the problem, right? So now we're able to specify tasks in a formal way, so we are kind of like absolutely sure of that of the task that we want the agent to solve, and we're able to translate that into a reward function which the agent actually understands. Now, the second problem is now how do we actually learn to solve these tasks without having to learn pi star, the optimal policy for every single one of them? So we need some general method to achieve this. Now, a popular way to do this in prior works, and this is like very popular in reinforcement learning, it is the idea of using options. And essentially, options are kind of like are skills that you can kind of chain temporally. And so here, I kind of like just mentioning that this is essentially to address a curse of dimensionality with this sort of tasks. And I'm going to kind of like highlight this curse of dimensionality shortly. So for the task I mentioned earlier, essentially, or for the domain I mentioned earlier, you can imagine that the robot learns, oops, I'm skipping some slides. Okay, so you can imagine that the robot learns to go to a button, right? So that is one skill. Then you can imagine the robot learns to go to a blue region, that is a second skill. Then the robot learns to go to a cylinder, that is a third skill. So it learns those three skills and also called formally options in the literature. And now you want it to combine those skills to solve the given task, right? Where it needs to go to a button, then to a cylinder without ever entering a blue region. And so essentially you can decompose this into the following three things the agent needs to do. The agent needs to eventually reach a button that is not in the blue region. Then it needs to eventually reach a cylinder that is not in the blue region. And it needs to do all of this while always not entering a blue region. All right. So now let's say that we use the skills we have just learned, the options we have learned to solve this task. And what you quickly realize is that you fail, right? So all you can do with the skill that you have learned is to eventually reach a button, then eventually reach a cylinder, right? But you have not actually learned how to avoid blue regions, right? The skills you have learned didn't incorporate this notion of avoiding the blue region. And there's no way that you can address this using the skills you have currently learned. You have to learn a new skill that incorporates avoiding the blue regions. And that is the way you deal with this specific new task. Right? And so essentially, for every single new task, using like the prior works, you will, most of the times we run into situations where you need to learn a new skill to deal with the specific situation that that new task presents. Right? And so essentially, there's two causes of dimensionality present in temporal logic tasks. The first one is the special curse of dimensionality. Essentially, it says that there is a super exponential number of subtasks which the agent may be required to achieve. So like this, for example, is an example, right? If you have like p propositions, then there is 2 to the 2 to the p possible Boolean expressions over those propositions. Right? So that's a super exponential number of subtasks that your agent may be required to eventually satisfy. And then also you have the temporal curse, right? So there's also 2 to the p Boolean expressions that the agent may be required to not or to always satisfy while it is trying to solve a given task. Right? So that's again that's what we call the temporal curse. And so there's these two big causes of dimensionality that needs to be addressed when you are learning your skills, so that given a new task, you can now properly solve them without having to do any additional learning. You need to somehow first deal with these two causes of dimensionality. So I hope that kind of makes sense. So the way we deal with this is by introducing the notion of primitives. Is by introducing the notion of primitives. Essentially, for the special curse, we introduce task primitives, which are basically composable MDPs for eventually satisfying each proposition. Right? So, but when I say each time I say proposition, you can imagine like a button or like a blue region in that example domain I gave. Right? And then we define scale primitives to basically be word value functions for each task primitive. Now, word value function here is a new term. What does that essentially mean? So this is a type of knowledge representation I introduced in prior work, which basically encodes general knowledge about the environment while learning each specific task. And so this was called, I talked about that at the RLTM conference in 2022. And basically the intuition is simple. While solving one task, we should learn about other tasks that we may need to solve in the future. How do we achieve this? We do that by essentially doing a simple multiplication on the task reward function. So what we define this extended reward function that basically gives a large penalty if the agent receives unintended goal states. Otherwise, it just receives the regular task reward. So this R here is a regular task reward, and this R min here is a huge penalty that you give if the goal state the agent has reached is not the goal that it wanted to reach. Right. So that is the only modification we do to the task reward function to make it goal based. And now we learn a policy for that new reward function. And we can also like learn an action value function for that new reward function. All right. And this is what we call a word value function. And the reason why we call it a word value function is because from this simple modification, the agent is able to learn how to achieve any goal in the environment. So imagine, for example, this simple video game domain. You have objects here with various colors and shapes, right? Boxes, circles, and so on. And so imagine that you want the agent to go off like learn the skill for collecting blue objects. So you can go to blue cylinder, to the blue circles, and you can go to the blue squares. Now, if what you are learning is a word value function for this, then what you will learn is something that looks like this, right? You would have learned how to achieve all of the objects in the environment, even though right now the only thing that you really need to solve is going to blue objects. But you are still learning a general knowledge about how to reach all the other objects and also the value of achieving them. Right? So you can see that the value for objects which are not blue are low. Right? So they are bluish here. So they have like a lower values, and the ones associated to blue objects have a higher value. And then if you actually want to now generate the policy to actually solve the task that you wanted to solve, you just maximize over goals. And what you get is this regular value function. Right? You see that it's like high when you are at the blue objects, and it gradually gets closer to that, no matter which position you are in the environment. Right? So that is the regular value function which you will actually use to actually act greedily and reach whatever was the goal for the blue task. But the important thing here is that to do this, we didn't go straight to learning this single value function that is very specific to this task. We first learn a word value function, and that is what is going to enable us to achieve a compositional generalization in reinforcement learning. Okay, so that is it for the task primitives and skill primitives. So what we now do for the domain I introduced earlier is we will learn a word value function, a skill primitive for going to buttons. We will learn one for going to blue objects and to the blue regions. And we will learn one for going to the red cylinders. Right? And now that you have learned these three ones, using prior work, this is the Boolean test algebra which I presented at New Web 2020. Using that work, I basically showed that you can achieve optimal composition if you have learned word value functions. And so to kind of like solve any Boolean expression over these three propositions, you do not have to do any additional learning anymore. You can actually recompose these three scales to solve any Boolean expression over them. So how do you actually do that? So I'll just explain that at high level in the next slide. But before that, one key aspect of this which I need to mention is how do you address the temporal curse of dimensionality? And then we address it by introducing this notion of constraints. And the idea here is very simple. So constraints are propositions which the agent may be required to always keep true or always keep false in an episode or in a temporal logic task. Right? And we are basically just going to use this to augment the state space of our task primitives. So what does this look like? So imagine, for example, that we are looking at going to a cylinder, right? And the constraints set that we set is blue regions, right? So here I'm showing the trajectory of the agent and the goal it has reached. And so you see that it has reached a button, it has reached a cylinder, and while doing that, it has broken the blue region constraint. Right? So that's included in the goal it has reached at the end of that episode. Similarly here, we see that the agent has gone to a button and to a cylinder without crossing the blue region. And so the goal only reflects the button and cylinder that it has reached. So that is the second modification we are doing to be able to address the temporal curves. Because now the agent is aware of which propositions or which constraints it has broken during the trajectory in an episode. So when learning, let's say, to reach a cylinder, it can, again, if you are learning word value functions, when learning to reach a cylinder, it is going to learn both how to reach the cylinder while breaking the constraints and also how to reach the cylinder without breaking the constraints. It's going to learn all of the possible goals that are achievable in this environment. Okay, so I hope that kind of makes sense. So after you have learned these scale primitives augmented with these constraints, how do you actually do composition on them? So we'll just explain this at a high level, and then we will move on to seeing the results. So imagine that you have two task primitives, and these are MDPs. So MDPs are called Markov decision processes. It is basically the way we formally define a reinforcement learning task in RL. So you have like two MDPs here, and then you have their reward functions, A and B. So the way you compose these task primitives is as follows. So you can say, for example, if you want to do A or B, then it is just defined by maximizing over their rewards. If you want to do A and B, so their conjunction, you just minimize over their rewards to obtain the reward of the conjunction. And to the negation is just a constant minus the reward of the task you're negating. So that is how we define the Boolean algebra over MTPs. Now, let's say you have learned scale primitives for each of these task primitives. So you have learned scale primitive A and B. You can obtain the corresponding scales by composing them similarly, right? So to solve the task A or B, you just compose the scale primitives A or B by just applying the same operator, so maximizing over the word value functions. Similarly for conjunction, to do the conjunction of A and B, of A and B, then you just minimize over the word value functions. And to do the negation, you just take a constant. This is a constant word value function, and you subtract that, and you subtract your word value function of A from that constant. Right? And that is essentially it. So that is how we do composition, at least logical composition. Now we're going to leverage that to address the original problem of being able to solve temporal logic tasks. And the way we will do that is by introducing this notion of scale machines. So in simple terms, a scale machine is a finite state machine that encodes the sequence of scale compositions to use. Right? So imagine, for example, that you have a reward machine here. So this is the reward machine I showed earlier for the task of going to a button, then to a cylinder without entering blue regions. So that is the reward machine for it. What you can do is you can plan over this reward machine using, let's say, value iteration or any other planner you prefer to then know which scale to use at each node. So let's say we plan over this reward machine. What we'll get is something like this. So in this case, I use value iteration for the planning process. So at U node here, I know that if I reach a blue region, it will have a without that is not in a if I reach a button that is not in the blue region, it will be have a value of 0.9 with respect to the final trajectory I want to take, right? And so on. So this trajectory here, or this transition here, we have a value of 0.1. This transition here has a value of 1 because that is actually the transition that solves the task, and so on, right? So with this value iteration or value iterated reward machine, I can now pick greedily the scale I want to achieve at each node. Right? So, for example, at U node here, I know that I want to achieve this scale because that is the one with the highest value, right? So I want to achieve button and not blue region. And so I compose my scale primitives to achieve that. Right? So I take the scale primitive for button, intersection, the negation of the scale primitive for blue region. And that is going to give me the policy for eventually reaching a button that is not in the blue region. Also, I take the conjunction of that with not breaking the blue region constraint, right? Because I do not want to enter a blue region while I'm trying to achieve this guy here, right? Otherwise, I will fail the task. I will reach the terminal state. So that is how we move from a reward machine to a skill machine. And the same thing happens here. So here, I see that I want to achieve this skill here. And so I compose the scale primitive for reaching a a cylinder. I compose that with the scale primitive for not reaching a blue region, and then also make sure that I do not break the constraints, right? And that is what a scale machine is. So I hope that kind of makes sense. I think this is the cover, the most involved slide everywhere here. But at a high level, you move from the task specification, which was to go to a button, then to a cylinder without breaking decorations. You go from that, from the formal language specification of that, to a reward machine, which you can always do. You can always convert any formal language to a final state machine. Then you plan over that reward machine to know the value, how valuable is each transition in this reward machine. Now that you know how valuable each transition is by planning, you can then gradually determine which scale do you want to execute at each node of this state machine to eventually solve the task. And that is what gives you a scale machine. So I hope that kind of makes sense. Yeah. So if you execute a scale machine in the task that I just showed, then you see the agent is able to go to the button and then to a cylinder while avoiding the blue region. And again, this was just from learning the three scale primitives and then composing them as required for the specific new task. All right. And we showed in the paper that this whole process enables you to obtain near optimal policies for any new task. It is guaranteed to be satisfying under some reachability assumptions. So reachability assumptions here basically is just saying that at each state in your environment, you can achieve uh, any transition in your in your state machine that represents the task. So that is the reachability assumptions. Under those assumptions, you are guaranteed that the policy generated by the skill machine is going to be satisfying. It is going to actually solve the task. Not necessarily optimally, but it is going to solve the task. I'm showing here another example without having to do any additional learning. Right? So you are presented with this new task to navigate to a hazard, then to a cylinder, and finally to a cylinder again. And finally to a cylinder again while avoiding hazards. Right? So this is the formal language specification of it. And the skill you get from the policy you get from your skill machine actually solves that task. It goes to a blue region, then to a cylinder again while avoiding the blue region. And this was done without doing any additional learning. Right? And so you can solve essentially any new temporal logic task without having to kind of like spend enormous interactions with the environment to do reinforcement learning from scratch. I hope that kind of like makes sense. So we have solved the two main challenges we kind of wanted to solve here. The first, to specify tasks in a human understandable manner by using formal language. That actually is what has been done in the literature for a while now, so that is not new to this work. But the second main thing was that now that we're able to specify tasks using formal language, can we solve each of those tasks without having to do any further learning? And we were able to do that by introducing scale machines. So I hope that kind of makes sense. Let me look at the time. Okay, let me show some quantitative examples and then that will pretty much be it. So the other thing here I mentioned is that we make some assumptions here in our theory, right? And the main one was that um, the transitions in the state machine should be reachable from any state in the environment. And the second is that because you are picking the skills greedily, right, because you are picking the skills to execute at each node greedily, you do not have the guarantee of optimality. Right? You are going to eventually solve the task, but maybe not optimally. So what if you actually want the optimal policies? Then you can do feature transfer. You can use any RL algorithm like Q-learning for those who are familiar with reinforcement learning. You have heard of Q-learning before. For those who are not, this is just like a reinforcement learning algorithm that enables you to learn the optimal policy for a given task. Right? And this is going to be a policy that is going to be specific for that task, right? Like I mentioned in the introduction. And so what you can do, so here, let's consider the office work domain I mentioned earlier. And let's say that you are presented with this task, right? Deliver coffee to the office and never break a decoration. So essentially means eventually deliver coffee and next go to the office, eventually go to the office and do all of that without ever breaking a decoration, right? So let's say that for this task, you do the same process I mentioned earlier, right? You translate the task into a reward machine. So actually here I've swapped the reward machine with the value iteration. So this is the reward machine here. From the reward machine, you do planning to know how valuable each transition is, right? And then from that, you greedily select the scale you want to use at each node, which gives you the scale machine. So this is the composition of your scale primitives that you're going to execute at each node of the state machine. And then if you execute the policy that you get from this, you get what you have on the left here. And so you see that the agent is taking the long way around to go to the coffee and then to the office, and it is doing that while avoiding these decorations. All right. But this is not the optimal way of solving this task. But then you can, starting from the performance of this zero-shot policy, you can do few-shot learning to actually obtain the optimal behavior, which you see on the right. So now the agent is able to go to the coffee, which is slightly further away from the coffee that was here. So the reason why it was picking the suboptimal path here is because this coffee was slightly closer to it than this coffee here. And so because it was kind of like just greedily picking what is the scale to use right now, it went through this suboptimal path. But by just doing a bit of few shot learning, it is able to go to the coffee which is further away. But after drinking that coffee, the office is much closer to it. Right? I hope that kind of like makes sense. So if you look at this quantitatively, everything here is prior work, right? So here I'm basically showing so the x-axis here is like hundreds of thousands, yeah, hundreds of thousands, and what I am showing here for with this black line here is a number of time steps or interactions with the environment it took to learn the skill primitives, right? So we first learn how to reach decorations, how to reach room A, how to reach coffee, office, mail, and so on, right? And we learn all of that using 100,000 interactions with the environment. And then this is the performance that we get from the skill machine without doing any further learning. Right? So this is the performance we get with this zero-shot policy here, this flat line here. When we do some additional learning, so kind of like obtain the optimal policy, what you get is this curve here, which starts from your zero-shot performance and then just improves from there to the optimal one, right? Meanwhile, if you look at all of the other prior works, although some of them learn much faster than the other ones, they still have to do learning for every single new task, right? Like this one, for example, is learning extremely fast. Right? In the same amount of time it took us to learn our scale primitive, it has already reached this performance here. But this is the performance it is learning. This is the policy it is learning for this specific task. Um, Meanwhile, using our approach for any new task, we get basically this behavior. We start from a very high performance, and then you can fine tune that to get the optimal behavior. I hope that curve makes sense. So if I go back to the original task I showed at the beginning of this presentation, which was this very long task, right? Deliver mail to the office and so on. Then this is the policy you get from your skill machine, right? So it starts by going to the mail and deliver mail to the office until there's no mail left. Then deliver coffee to the office until there is no person in the office, and then patrols each room and back to room A, right? And it is able to do all of these new tasks, even this extremely long one, while avoiding the decorations, which are the safety constraints you have put in the task. All of that without further learning, right? By just recomposing the skill primitives it had learned for each proposition in the environment. I hope that kind of makes sense. So that is essentially this work that we did. And in this case, I've been demonstrating it using like navigation type of task, but it's a fairly general framework, right? So this is applicable to any domain, any environment that you're interested in, where you can specify tasks using formal language. Right? And that is pretty much it. So quantitatively, what you see flat here is algorithms which are guaranteed to converge, but they're just extremely sample inefficient, right? So even though they're guaranteed to eventually converge as t turns to infinity, as the number of interactions with the environment turns to infinity, in practice, they are just extremely bad because it will take ages to converge. What you see here, these two curves here, are kind of like methods that use the options strategy, right? But they start with poor performance and they learn fairly fast to solve the new task, but they have to do learning, right? Because of the issue I mentioned earlier. The skills they learned were not able to kind of like solve this specific task, and so they had to like fine tune those skills or learn new skills. But using our approach, we're able to start from the get go with very high performance. And actually, in this case, the performance we got from the skill machine is optimal. Doing additional future learning on top of that, it gives us no benefit in terms of learning. What we had before was always optimal. Cool. So I hope that kind of like demonstrates this research we did. And so to kind of conclude all of this, skill machines, so I introduce skill machines, which enable zero-shot, near optimal temporal and concurrent composition. Concurrent here is like the logical or spatial aspect of the problem, and temporal here is how you need to do A, then B, then C, and so on. I showed how this can be learned directly from a reward machine and are satisfying. Right? So you given a new task, you can do planning on the reward machine. So given a new task, you can do planning on the reward machine. Or you can translate that to a reward machine, do planning on it using, let's say, value iteration to obtain a skill machine. All right. Also, before even seeing any task, you can just take your environment, you learn the skill primitives, and then that gives you the skills that you can use at each node of your state machine, right? And then using these two components, to obtain a skill machine, you can then use a skill machine to solve any new task without further learning. Cool. And you have guarantees on the behaviors, right? So you have that if the reachability assumption holds, then the policies you obtain from a skill machine are going to actually solve the task without further learning. And we also showed that if they're not optimal enough for you, you can use any traditional reinforcement learning method to start from the zero shot performance and improve from there to the optimal performance. And that is it for this presentation. Thank you guys for listening, and let me know if you have any questions.
Thank you. We are the ones to thank you for the very interesting presentation. Um, so, if there are any questions, please type them in the comment section. Please, 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 please. I have a very first question. Can you go back to like the second slide or so?
That's it.
Okay, just so that we make it clear, I am not a. I have never worked with reinforcement learning, though I kind of know the principles. So my questions will
Mm.
be really basic.
That is completely
So
fair.
already accept my apologies.
I know these are
Okay,
the
the
questions we
slide
look.
after this one,
So let's
actually,
see.
yeah. Because when you presented this in the sense, okay, we want the agent to do one, two, three until there is no more person in the office, until there is no more, etc. I was thinking, what happens if you just use an if rule based statement?
Mm, that's a very good question.
Like a
So
very naive, as naive baseline, what happens?
yeah. So then what we do is so for this specific task, um, you'll be giving it as a formal language, right? So you can convert that to, let's say, a state machine. Let's say it's at this current node. This is what will happen if you take a particular step in the environment, right? And then you will reach this other node. So then you can maybe use that to build your if else statement for what to do. But then the question is that the agent here first, this is model free, so you don't have access to what is the dynamics of the environment. So, like, you don't know at this current stage here what if I move my joints this way, or for example, in this case, if I take the forward action, which is the next set I'm going to reach, right? You do not know that, and so if you kind of like want to say that starting from this position, oh, what am I pointing? If you want to say that starting from this position here, I want to first reach what is this saying? So deliver mail to the office until there's no mail left. So you want to write if else statements that we move the agent from here to
Yeah,
there, right? But then how will you actually write those if else statements without actually knowing that the environment looks like this? Because
yeah,
remember, the only thing the agent sees is like its current position, XY coordinate, and then it can take actions up, left, and down.
okay,
That's all it sees. Right? And
okay.
so us as a human being, we are seeing this whole map of like, and then we can plan in our head. Right? You can imagine the agent moving, and then reaching the mail. But the agent doesn't know that policy. Right? That is in fact the policy right there. How to move from that position to that mail.
Okay, so if I understood correctly, the agent doesn't know where each of these things are. No.
Yes, it has to like learn it.
Okay. By navigating through it, and then after some iterations, it then knows where everything is, and then you optimize, and then optimizes the path to do whatever thing it has to do.
Y- Yes,
Okay,
exactly, exactly.
makes sense.
And then there's the second aspect of that is, and this is kind of like what I was kind of alluding to with regular reinforcement learning, is that let's say that you do that learning, so you do like after a couple of interactions with the environment via trial and error, you kind of like finally learn the policy for kind of if you are in this position here, I need to take the up action, then the right action, then the up action, and so on. You kind of like learn that policy for reaching the mail location, right? That is one policy you have learned for this very specific goal you
Okay.
wanted to reach. Right. Now, imagine the number of possible goals that you need that you may need to conflict to reach in this environment. You have how many objects here? You have 10 of them. Right? So you have A, B, C, and D. So that is four. You have decorations, this five. You have coffee location, six. You have the office and mail location, that makes eight. And then
Yeah.
you also have propositions for whether or not there's people in the office or whether there's mails in the office. So there's 10 total propositions, or let's say sub goals that you may need to reach in this environment. And then you kind of imagine the number of Boolean expressions over those 10 propositions, because one goal could be that you want to reach A or D, right? And so if you are here, you need to go to D. If you are here, you need to go to A. If you are doing A or D.
Yeah.
Um, and that is just one Boolean expression over your 10 propositions. How many such how many such Boolean expressions are there? There
Yeah,
is two
that's
to the
when you were talking about the curse of dimensionality. Kind
exactly. So that is kind of what this whole approach was trying to deal with.
And so, yeah, in your approach, I mean, that was the subject of the presentation, but just in layman terms, what does your approach then do instead of
Yeah,
like doing a multiplicative, I mean, instead of looking like all the possible configurations?
yeah. So because of that cost of dimensionality, that conflict shows that there is this super exponential number of Boolean expressions that you may need to achieve. And also there's like this super exponential number of Boolean expressions that you may need to not achieve, right? So for example, while solving this task, you needed to not enter a decoration, for example. Um, so because of that, the strategy that we went with this method is to say we are going to learn decomposed knowledge, right? So we are going to learn how to reach each proposition, how to reach room A, how to reach a coffee locations, how to reach mail locations. We're going to learn each of those 10, how to achieve those 10 propositions, but we are going to learn them in a way that they are general, in a way that given any new specific task, we can recombine those that knowledge, right, those policies to obtain the specific policy for the new task. Right? And so that is a kind of like in the briefest term what we kind of like did here. Right? You do not learn skills specific to each new task because that is going to be you have that cost of dimensionality. You instead learn decomposed knowledge, which are related in some way. Right? In this case, they are related by the environment in which you are learning them, and they
Yeah.
are related by the kind of like number of propositions in the environment. So you learn those decomposed knowledge for achieving each proposition, and then you recombine those knowledge when presented with any new task. And that recombination is where you do that Boolean composition stuff which I mentioned.
So is it kind of like you're learning? Is I mean, it just sounds like a large purpose. Let's just translate it to what is famous now in AI. Like you're learning a large purpose language model, which can then do multiple downstream tasks depending on, yeah, the interest of the user.
Yes, yes, yes. That is a that's one way of putting it. We've got like guarantees in the behaviors you get because one thing that you could actually do is you could take a huge neural network.
Yeah,
You could take a huge neural network and just pre-train it on a number of tasks, right? And that is kind of like the way current machine learning or like large language models will do things.
yeah.
You take it and you pre-train on a whole bunch of tasks, and then when presented with a new one, your hope is that it's going to generalize to that new task. Right?
Yeah.
Um, but that is a hope. So the second aspect of this was to be able to do this in a way that you can actually guarantee the behaviors you are getting.
Okay. But I guess, like you said, these subtasks are somehow related because I'm thinking, what happens if they are very different from each other?
Yeah, and so that is kind of like the what grounds them here. It is the fact that they are all happening in the same environment.
Okay.
And that environment can be as general as you want, so long as it is the same environment. So it could be the
Okay.
real world, for example, right? And that is as general as you can get. Of course,
Okay.
like that will mean that learning each individual skill will be expensive because the real world is very complex. Right? But that is what grounds them in their similarities, that they happen in the same environment. Yeah.
Very
And so
cool.
in cases where you want them want to transfer to different environments, this completely won't work, right?
Yeah.
If you train this in a video game like in Atari games, and then you kind of like now go to um, a text-based world games, right? Maybe like you are in the ChatGPT setting, completely won't work. Or you apply it to a real robot when you have trained it in video games, completely won't work. But if your setting was already the general setting, if your setting was like the robot is like a human being, it can play Atari, it can play, it has like actions to be able to like play Atari, it has actions to be able to navigate in the real world, it has actions um, to like type a keyboard and like answer stuff using
Yeah.
text, then it's going to apply to that setting. So it all depends on the environment in which you have defined.
And as you said, an environment can be then multiple things at the same time. Okay.
Yeah.
Well, perfect. Some point in the beginning of the presentation, you said something like another drawback of the current literature is that um, the agent can learn a different reward function than what is actually being wanted.
Yes. So if I understand correctly, the part you are referring to, it was like this idea of learning to compose knowledge and then recombining them for each specific task has been
Yeah.
explored in literature before, but the only way they have looked at the decomposition is in the temporal aspect.
Okay.
So, like, I want to learn how to do A, I'm going to learn how to do B, and then I can do A, then B. Right? But when they're now in a situation where they need to do A while not doing B, so do A and not B, they're not
Yeah.
able to handle that. So that's a
Okay.
new kind of like can think of that as a new reward function, which what they have learned is not able to adapt to. And so they have to now learn a new skill of A and not B,
Okay.
if that kind of makes sense.
Yeah, yeah, yeah. Totally. Okay. Uh, I don't want to have the monopoly of questions here. Are there any questions from the audience? Please type them in the comment section. Okay. We have one from Willie. Very nice talk indeed. What is the key difference between temporal logic and formal logic modeling? I guess both concepts lead to the final state machine. I missed some parts of your talk. We're sorry about
Okay.
that. He's probably busy because otherwise he would be fully on the.
Exactly. I mean, this is a difficult time for all of us for presentations.
We are managing.
So yeah. So to thanks a lot for actually finding the time to at least to listen for some parts of the presentation. So what you are saying there is so in the case of formal logic modeling, so you're also kind of like using leading to state machines, but I guess there's no real difference here. Right? At the end of the day, that is speaking to the way you are specifying your tasks, right? So you can use formal logic modeling to kind of like maybe learn the state machine that represents what you want the agent to solve, for example. Um, and in the temporal logic I just spoke about, that was just to say that, for example, linear temporal logic is one type of formal language that you can use to specify a task. Right? So it has like temporal operators like then, eventually, always, and it has logic operators, right, like and or not, and uses that to specify. You can use that to specify a task. And so yes, so all of those basically speak to the task specification. Once you have that specification, then our method can be used, where what we do is we say all of those specifications are over what the traditional set. And so imagine like what objects in the environment in the case of navigation, and you learn skills for each of those. And then you, using the state machine that represents the person itself, you can plan in that state machine to determine what do I do now, then what do I know do after that, and what do I do after that. And once you kind of finish planning, you know what to do, you then compose those state units to actually generate the policy for cover each of your problem. So the course for the large majority of this presentation was on once you have the state machine representing the task you need to solve, how do you then generate the policy for solving that task? Uh, so the general framework pretty much looks like this. Yeah. I don't know if that kind of answered the question, but let me know if I kind of misunderstood the question.
I guess he
Uh,
will do.
yes.
I have another question. The slide where you present the archive 2022 reference, where you were actually introducing the problem and showing that though the agent was asked not to go through the blue region, it still went through it.
Yeah. Let's see.
Yeah, here.
This one. Yes.
Yeah. So because the last item, the last task or rule given to the agent is you always need to move away from blue regions. But
Mm.
why was the agent then going through the blue region?
Yeah, so very good question. So the reason why the agent is still going through the blue vision share is because so what it has learned, so this skill, at least from the way previous work learns this skill, is they learn a policy specific for this skill, right? So they will learn, for example, that for going to a button, no matter where I am, so they will learn so that they don't have a model of the environment, right? So they go for with trial and error after interacting with the environment for a period of time. They will learn that if I'm here, then I need to move like this to reach here. If I'm here, I need to move like this to reach here, and so on. That is what we learn for this guy, and that's the only thing that we learn. That's specific policy. And when learning to reach a cylinder, they will learn that if I'm here, for example, the shortest path to reach a cylinder is to go like that. Right? That is what we're learning in that, like when we're learning this skill. Right? And then they also learn how to go to a blue region. So they will learn that, for example, if I'm here, then I need to move like that to reach a blue region. Right? But then the problem, so they learn a specific policy for those specific skills. But then the problem with that is now that they need to solve something that requires them to not to stay away from the blue region. The policy they have learned, which was if I'm going to a cylinder, I just move like this,
Yeah,
is unable to adapt to this new situation, right?
I
Now
see.
they have to like replan. They have to like do again trial and error to see that, oh, if I move like this under the reward function of this task, I failed the task. I need to move like that. And so they need to spend a whole bunch of environment interactions to learn that via trial and error. So that is why they fail because they are not learning general policies. They're learning uh, a specific policy for that specific skill they want to learn.
Okay, let me maybe ask another question just to be sure I understood it, like in very simple terms. So, in reinforcement learning, you have the agent, the state, and the reward. So, the agent, the actions, and the reward. Okay, so in this situation, does it mean that when the agent was learning to move from one point to the cylinder, though it
Mm.
was crossing the blue region, it was still receiving a positive reward because it eventually did the task?
Yes,
Okay, so because the task was very specific, was the cylinder.
yes,
Okay, and so it means that to move away from the blue region, then it needs to learn a new kind of a new task where now it will be penalized if it goes on the the blue region.
yes, exactly.
Okay, okay. Okay, so your idea is you can actually learn everything within this environment if you specify this correctly with. Okay,
Yes, exactly.
okay.
Yeah. I also see that my battery is running low, so I'll just turn the camera off for a bit to go and plug in my laptop.
It's
But I'm still listening. I am still here.
yeah, yeah. Um, so are there any other questions in the chart? Are there any other questions for Geraud, please? Willie has another question. He's
Okay.
saying, I could be wrong. So at the end of your learning, will you have a final optimal state machine?
Um, let's see. So I
You
could
can
be
come back. You
wrong.
can
So
take your time. Don't worry.
yeah, no, no. Let me think about this. So at the end of your learning, will you have a final optimal state machine? So essentially, the way, so I'm about to say yes, but as you call for GD to be a bit more precise on what you are getting at the end of learning. Oops. So I see the screen share has stopped. Let me just put that back quickly. But essentially, at the end of your learning, what you will get is a satisfying policy. Right? So you'll be guaranteed that the policy you get, under some assumptions, the policy you get is going to solve the task. for any new task. Um, but if you kind of want to have the optimal policy, so I showed some examples earlier where the policy was solving the task, but it wasn't optimal. It was picking the longer trajectory. If you want to guarantee that you are going to get the optimal one, then you can do additional learning on top of that policy to learn a specific policy for that specific task. And you can do that much faster starting from the policy that our approach gives you. So that is kind of like the slight correction I will do there is that the policy you get immediately for any new task under some assumptions will solve that task. But if you not satisfied with the optimality of that policy, you can do some additional learning. Yeah, so I was showing it here. So you see, for example, this is a policy you will get from our approach without doing any further learning. Right. So but it takes the longer path to go to the coffee, then to go to the office. But then if you do some additional learning on top of that, then it will kind of go to the coffee that is a bit further away from this coffee here, but uh, then it goes to the office which is closer to it. So this is a much shorter path than the one that our zero shot policy gives you. But both of these are our method. This is just what you get without doing any additional learning, and this is what you get after doing a bit more learning on top of your policy.
Cool, cool.
I don't know
I
if that
have,
answers this question. So,
uh,
so this, so what you have learned here is not optimal. It is satisfies, but you can do few short learning on top of that.
yeah, I think that's yeah, think that's a good enough answer because yeah, I kind of understand. So
Nice. That is
um,
us.
I have maybe one last question.
Hmm.
The reward machine, but not on this slide. On another slide where you have like um, probabilities. Yeah,
Okay.
yeah. So I get the reward machine is the one on the left on the far.
Yes, I swapped this.
Yeah,
I swapped this to so actually it is this one. Let me go to one where I didn't mess up my slide. So
yeah,
let's take
yeah.
this one.
So I was wondering, how do you move from the reward to the value iteration machine?
Okay, so just plug in my laptop.
Yeah.
Um, so sorry, repeat that question.
Yeah, I was wondering how do you move from the reward to the from the reward machine to the value iteration?
Okay, yeah. So essentially, what you see here is so basically value iteration is like a planning approach in reinforcement learning. But let's say that we're not even using value iteration. We're just like planning, right? So you're just
Okay.
doing trial and error to find out what is the shortest path from your starting node to the most rewarding to like the node or to the transition that has a reward of one. Right?
Okay.
So if you are here, you go off. Okay, let's just start here. If you are here and you take this transition here, you're always going to get a reward of one. Right?
Mm-hmm.
So that is how we get this one here. If you are here and you do this transition here, you get a reward of zero. Then, so this is also discounted. Right? So like you have a discounting of 0.9 for each step you take. So if you are here, you take this transition here, you get a reward of zero. Then if you take now the best transition here, you get zero point 0.9 times one. So that is how you get zero point 0.9 here.
Okay.
If you are here, you take this transition here, you get a reward of zero and you terminate. So that is why you have zero here. Same thing here. If you are here, you take this transition here, you get a reward of zero. Then, if you take the best transition, which is this one here, you get zero point 0.9 times one. And that is why you get zero point 0.9 here. And finally, if you are here and you take this transition here,
Yeah.
then follow the best path, which is going like this and then going like this, what you get is 0 plus 0 plus 0.9 to the power 2 because you have taken one step, two steps, or you have taken one step, um, and the current step is not discounted. So one step, then two steps, three steps. So you take gamma, which is you are discounting. So it's 0.9 to the power of 2. So that is the number of steps you have taken, excluding your current one. And that is what you get. That is why you get 0.81 here. So 0.81 is just 0.9 to the power of 2. That basically represents kind of like a discounted notion of the probability of going from the current state to the um, best transition following the optimal path. And so that is just like regular planning that we give you. That if you use like something like A star, for example, for those who are familiar with like graph planning, like shortest path planning.
Okay.
So that is what we get.
Because I was wondering, like, which step throughout the whole learning is the one that takes the 15,000 iterations?
Uh, or you mean the graphs are showed near the
Yeah,
end?
because you said that your algorithm first takes 15,000 iterations was it to learn the environment?
Oh,
And
let me go back there.
yeah,
Uh, okay, so here,
yes, yes, the line.
yeah. So the algorithm takes so this is 100,000 iterations.
Yeah, a
So
hundred
it takes
thousand.
It takes 100,000 iterations to learn the scale primitive. So to learn how to go to room A from any position, how to go to the coffee locations from any position, and so on. So for each of these objects or propositions in the environment, so there's 10 of them in total. Um, it takes it 100, or we give it a budget of 100,000 interactions to learn the policies or to learn the word value functions for them.
Oh, you give it a budget, so it's not like so you decide the number of iterations you let it
Yeah,
on.
for this experiment, you could of course let it continue training until it converges to be optimal, but in practice, you always give like a budget for the training time.
Okay. I mean, if it's not necessary for it to reach convergence, then
Yeah.
and how much time can it take to do that? To learn
So,
the
mm. So it depends on the specific environment in which you are in, right? So for example, in the safety gym domain that I showed earlier, so in this domain, for example, it took like about 100,000 to learn decent policies that and they're not necessarily optimal, but
yeah.
they were good enough. Um, it took about 100,000 iterations, but for this one here,
And how much time is that? 100,000 iterations?
oh, it's 100,000 times step interaction interactions with the environment.
Yeah.
Uh, so in practice, that will depend on your CPU or like how fast your computer is. But in terms of the
Okay.
environment, it is basically like if the agent moves from there and it takes a right action and then it is now there, that is one interaction. If it moves from there, takes a right action there, that's a second interactions, and so on. So it took 100,000 of those
Okay.
to learn. Yeah,
Okay.
and
Yeah.
you can see compared to regular Q learning for this specific task, so it took 100,000 to learn the scale primitives. But when learning to solve this specific task, Q learning, which is this guy here,
Yeah.
uh, took way more than that to
Yeah.
learn how to solve this specific task. All right. So that is kind of the at least like the relative difference in number of time steps.
Yeah. I see. So Willie has another question. Can you comment on the complexity of the time and space of the state machine?
Okay, just powering this laptop. Uh, so can you comment on the complexity of the time and space of the state machine? Let's see. So the time complexity is in terms of number of let's see. Okay, so let me, because like the time complexity of a given RL algorithm will depend on of course the specific environment and the specific algorithm you are using. So if we speak in terms of the state space, right, so we can like maybe speak in terms of the space complexity instead, and that is also directly proportional to the time complexity. So how large the state, if the state is very large, if the state space is very large, then it will take longer for an other algorithm to train there. So in terms of the space complexity, it is number of propositions is kind of like it's a function of the number of propositions, which is because we want to learn scale primitives for each one of them. Um, and so it is 2 to the power p, but it is the dimensionality of a state space, which is, let's say, cardinality of S times 2 to the power p, which is basically all the possible goals you can achieve for each primitive. Actually, you take that times the number of primitives you want to learn, which is also p. So it is cardinality of the state space times number of propositions in your environment times 2 to the power number of propositions in your environment. So it is linear in the size of the state space and exponential in the size of the propositions in your environment. Um, and that is kind of like, so basically this whole approach drops one exponential in time and space complexity because remember the total number of possible Boolean expressions which you may be required to solve in a given task is 2 to the 2 to the p. Uh, and you have that both for the spatial curves and also for the temporal curves. So we drop one exponential in the time and space complexity. Of course, this is just speaking with respect to the skills you are learning, and that can then be composed together. If we look at this in terms of, if you compare this in terms of what is the size of your task space, like how many possible tasks can your agent be required to solve, well, that is infinite. Right? So this is infinitely better than not. So using composition is infinitely better than not using composition because there's infinitely many tasks like this which the agent may be required to solve. And so if you're using something like regular queue learning or any of these approaches actually which do not leverage or do not address both the spatial and temporal curses, uh, what you would have is an infinite sample complexity if you are kind of looking at generalizing over the whole task space, right? Because you have to learn for every single one of those. But if you are comparing with, if you are comparing, so this if you are comparing with like traditional methods, if you are just looking at the absolute time or space complexity for this approach, then yeah, it's exponential in number of propositions and linear in the state space. Well, actually, so there's this resource on complexity of learning algorithms in R. Usually, you can kind of think of usually they're quadratic in the size of the state space and the action space. But that is going into much of the details. Suffice to say that as a function of number of propositions in the environment, um, it is exponential in terms of that. And but compared to the total number that you have to deal with, it drops one exponentially in that because normally you have to like learn two to the p number of scales.
Okay. I don't know if that answers Willie's question. If that is the case,
Yeah, I hope that answers.
um,
Actually, another way I can put this to, because I see we'll ask another question. Just to go off like quickly, add something else to this.
yeah,
If I say that the number of time steps for learning a given skill in a given environment, so like, learning a specific policy in a given environment, the time complexity is, let's say, n, right? Then the time complexity of this and space complexity of this algorithm is going to be um, it is going to be n times 2 to the p. Um, if the n, to the, n times 2 to the p times p. The time complexity, if you use regular reinforcement learning, is going to be n times 2 to the 2 to the p uh, times 2, basically. So that is kind of the comparison of time complexities. So the normal time complexity is super exponential. This method us drop one exponential, makes it an exponential time complexity. Okay, so that is pretty much it for that.
Okay, thank you. The next question from Willie: if you have a final state machine and new propositions, can the states of the machine grow?
Mm,
Willie is getting inspired by your answers. He just keeps on
awesome.
questions.
It is awesome to have as many questions as possible. Really liking the interesting questions. So for this last question, hmm, can the states of the machine grow if you have a final state machine and new propositions? Um, okay, so I'm not sure if I understand the question well, but if I interpret the question as saying that if you have a new task that has like a so the state machine for that task is different, right? It's like larger. Like so in this case, for example, I did not show the state machine for this task, for example. So the state machines for this one looks like this. Right? The state machine for this one here is very large. I don't remember again, or I don't remember exactly what is the number of states there, but it is not included here because it was just that large. Um, and our approach kind of like still work for this. So the size of your state machine will basically be exactly the same as the size of the size of the state machine for your skill machine will be exactly the same as the size of the state machine that specifies your task. Right? So both your skill machine and the state machine that specifies the task will have the exact same size. It doesn't matter how big the states are. The skill machine uh, can have the exact and will have the exact same size. Um, and yeah, and the approach will still work no matter that size. The one thing we mentioned though is that your propositions should not change because the assumption here is that uh, your total set of propositions in the environment should not grow basically, so it should not change because the assumption here is that you are learning this in the same or you are giving this task in the same environment. So uh, the assumption is that the set of all possible propositions in the environment do not change. Right? So if you define it to be very to be a small subset, and then now you want to define tasks in propositions which the agent has never seen before, then you will have to do few short learning, or you have to learn a skill primitive for that, and also fine tune all of the skill primitives you have learned before. But if you define your set of propositions to be very general, to just be like any proposition in the environment, and you use like a neural network to do functional approximation in that situation, then it is going to then it is still going to work. I hope that kind of like makes sense for this aspect for this point we mentioned on new propositions. Um, but if you mean new propositions in terms of the new task you receive, so for example, you can have a task that says um, like this task, for example, says like go to coffee, then to the office without breaking decorations. And this one has new propositions, right? So this one includes like mails, it includes like home locations A, B, C, and D, and so on. Right? And also the size of the machine states has also increased. Right? So the size of the machine states for this one is this. There's only one, two, three, four states. I mean, five states in this one, and three propositions. In this one, there's way more propositions. There's actually all ten of them, and the size of the state machine is also like extremely is very large, and the corresponding size of the skin machine is able to kind of like uh, match that size and generate this policy. Yeah, see, there's a new
Yeah,
question.
there is another question from Willie.
Suppose
So,
you have a state machine for a given set of propositions. If you are given a new unseen proposition, what would happen? Okay, yeah. So, yeah, so it is still going to work as I just mentioned. The under the assumption that under the assumption that even before saying the propositions of a specific state machine in your environment itself, those propositions still exist. Right? Even if they're not present, even if they're not present in a specific state machine, in a specific task, that is present in your environment. Because the whole way this approach works is like it tries to learn a general knowledge which is independent of any specific task, and then for a specific task it combines that knowledge. So even if it is trying to solve this task, even if you're trying to solve this task here that has these three propositions, it is still going to learn how to achieve all of the propositions in the environment. Um, and irrespective of the current task. And then it's going to combine that knowledge to solve the specific task. Cool. I hope that could have made at least some degree of sense.
that's what we hope to all the viewers. Uh, I hope you don't feel a bit more dumb today like me, but and
Oh,
that
that is
you
sad to hear.
and that you've gotten some good knowledge about state of the art reinforcement learning and um, states and learning generalization. So, or multitasking in reinforcement learning. So, if
Mm,
there are no more questions, then maybe we can call it a
I
day.
see. I see. Really ask
Oh,
like,
okay.
yeah. So that is actually very true, right? So you can kind of think of so there's several ways in which this can tie to symbolic learning. Well, this is symbolic learning actually, right? So like you are kind of like learning each of these skills that you are learning are basically symbols. You are kind of actually so you have like so your task space is symbolic, and you're kind of like making your skill space or your policy space also symbolic basically. Um, so actually, that's a very good point. One thing that I didn't mention or that we didn't do in this work is say that maybe from a natural language instruction, right? Maybe from this, not this. So imagine that you didn't know what is the formal language specification of the task. You were only given the natural language specification. Then maybe you then need to like do symbolic learning to find the formal language specification of the task in terms of like the various symbols, the various propositions and operators. So you will need to do symbolic learning for that. And then you will kind of like and then you can apply our approach to generate the policy for that. Right? So that's a very interesting work which we have like a preliminary results for Boolean and for natural language to Boolean expressions. We have like a workshop paper on that. Um, but we so since this work was just since we only published this work this year, we don't have natural language to RTL for trying to RTL, but the same approach that we did for natural language to Boolean expressions should also still apply here. And essentially, the way that will work, so one way you can do symbolic learning, uh, but is by kind of using large language models, where you can use like in context learning to train a natural language, like let's say like a transformer, like ChatGPT. You can train it using giving it a couple of examples for how to translate natural language instructions into formal language expressions, right? and and you can do that in a supervised way. You can do that using in context learning, which is what we did in the prior work. And yeah, so that is something that you can do, which is an interesting, it's an interesting direction. Ultimately, what I think of is ultimately for general agents, you should be able to just have the agent. The agent will be in their environment. They will be learning this stuff like what are the relevant symbols in the environment and learning the scale primitives for those symbols. And then they will also like be learning how to understand natural language by learning how to translate it to a natural language to some formal language, right? Because a natural language is very ambiguous. So you want to translate that to some formal language, and that will involve symbolic learning, symbolic reasoning, and so on. And while you're learning that, you're also learning this stuff like decompose general knowledge in the form of scale primitives. Um, and given any specific task, you will just combine your natural language understanding with the scale primitives you have learned to be able to generate the policy for that new task. And I think in some way that is how human beings work. Right? As we are born, we do not understand language at first, but because like learned through exposure with the environment, because learn the meaning of natural language. So if I tell you to do something, you understand exactly what I mean, and then you combine the general knowledge you have learned. Right? You have learned various skills throughout your lifetime. You just combine those to be able to like solve the specific new task that you are given. So that's covered my vision for reinforcement learning agents too.
Because the formal language, it's the means by which you can speak to the agent.
Exactly, right.
Okay.
Exactly. Yeah.
Okay. Because I also thought the same, that you can train a model if you have the natural language to the formal language translation or alignment. You can train the model to do some translation.
Yeah, yeah,
And
exactly.
then, yeah, anyone then will be able to, for example, if you commercialize this for anyone who doesn't like is versed with formal language, or humans will not want to, if they want their robot to do a set of tasks. For example, when you're speaking to Siri, but that's something else, you don't put it in a formal language, etc. It will be natural language. And so then the model can do the conversion and the robot can do the learning.
Generate the policy.
Yeah.
Yeah. Yeah, exactly. Exactly. I think that is at least my direction towards having general agents. You mentioned that we are going to come back to the problem of AGI, but I guess that is a long discussion for another time.
Kind of, because I still
Hmm.
have to go back home. But actually, today, or was it yesterday, I saw on LinkedIn, a post on LinkedIn. Yeah, it was yesterday, from Google DeepMind, where they were showcasing their robot playing uh, table tennis against different scientists. Did you see that?
I didn't see that particular. I've seen a lot of videos
Oh,
of works on like table tennis, but I didn't see that specific one from DeepMind. But I imagine that was a cool video. I tried to check it after this now.
yeah. They were kind of explaining that the robot can reach the level of yeah, medium human table tennis player,
Mm.
etc.
Yeah,
Okay.
yeah. It is impressive how far reinforcement learning is currently in terms of learning specific tasks. Because table tennis is like a specific task, and now you like you can imagine if it's able to like play table tennis, if it is able to uh, like go make a cup of coffee, it is able to go do chores, it's able to play chess. Like they even before that table tennis one, they showed how they were able to beat like world champions at Go. and so on. Which was it's an awesome movie that they did, like a documentary movie style that they did for that, like the RL agent they trained to beat the world champion at Go. It's a super nice movie that I recommend everyone to check out if they haven't.
Thank you for the recommendation. And it's Saturday night. I mean,
Yeah,
you can do that with some popcorn. Uh,
exactly. That's the best way to spend your Saturday night. Watch some
there's
RL documentary of robot beating humans and making them question their life choices.
okay.
Uh,
Um, just one very last question on my end to wrap up. Like, how much in terms of infrastructure does one needs to be able to train an agent like this? I mean, do you need like a lot of GPUs? Do you need like no?
yeah. Yeah, so it depends on the complexity of your environment. So then the nice thing with reinforcement learning is that you can start very easy and you can go very complex, right? Like the tabular domains I showed here, I trained them on my laptop or without a
Oh,
GPU. Uh, but they're fairly simple environments like this
yeah,
one. A very simple environment, so you can train them in your laptop. It doesn't involve like a convolutional neural network, for example, for image observation, because
yeah,
it only sits at discrete XY positions. Right? But now imagine that you were kind of like training the agent where what it says is like this picture we are seeing here. So like then you
yeah,
will need like a convolutional neural network, for
yeah,
example, for the perception and feature extraction. Right? Imagine that you were also giving it natural language instructions instead of the formal language stuff. Then we need to have like a transformer, for example, to do the
yeah.
natural language understanding. And then, so as your environment gets more and more complex, that is kind of like what will determine the type of model you use for perception and for functional approximation. And that will also then determine the degree of compute you will need. So I would say for something like what you saw here, you could do it in your laptop on your laptop. For this environment here, that is a continuous control environment, so you need functional approximation. So that one you need a NVIDIA GPU for that one, but
Okay,
just like even the 1060 will be enough for that. To train something like ChatGPT, you will need to uh, you will need to somehow figure out a way for getting Google or Microsoft to give you a whole bunch of GPUs to be able to train that, because like that is a huge number of parameters. So it depends on the scale of the environment. But this is what I love about RL is that you can do fundamental research without all of that. Right? You can do fundamental research by just considering simple environments, but make sure that your theory and all of that works irrespective of environments. And then you just then go off like your compute will then depend on the specific environment in which you are.
yeah. Being independent, it's best. Okay.
Exactly.
So we thank the speaker again. Thank you, Geraud, once more for accepting to present today and for the very, very cool presentation and the kindness in answering all the questions.
Thank you
So
very much for having me. Yeah, it was super
it's
cool.
our yeah, it was our pleasure. So we already tell the viewers that next week we already have our next presentation for next week scheduled. Yeah, that will be on kind of cyber detection or yeah, something around privacy. So please be with us next week, Saturday, same time, same place. Okay,
Awesome.
so we wish
See,
everyone a nice weekend and see you next week.
see you guys next week. Bye bye.